Hello everyone, welcome to the physics class. Uh, we have started the chapter magnetic effects of current, and in the last lecture we have discussed about the introduction, that is how this magnetic effect of current was discovered, that was discovered by scientists, posted. And then we talked about that we need to find one formula to find the magnitude of the magnetic field and as well as the direction of the magnetic field, right? So while discussing about that, in that regard we discussed about a law. The name of the law was Biot-savart law. If you remember, the law was Biot-savart law, and we have discussed all aspects of the laws, and we have already discussed about the proportionality constant and how the formula is actually dealing with the current, line element, angle. Every aspect of the formula was discussed in the last lecture. Okay, so we have very well elaborated, in an elaborated way we have explained the formula. So today's topic is basically how to utilize that formula for finding the magnetic field for certain cases. Okay, so today we will apply the Biot-savart formula. If you remember, the formula was ideal sin theta by r square. So this was the Biot-savart law. Now today we will use this formula and we will find the magnitude of magnetic field for certain cases. So let us take the first case. The first case is we start with the easier one. So to find the magnetic field at the center of a current carrying circular loop. Okay, so we will take a circular loop conductor which is carrying a current. Then what will be the magnetic field produced at the center of that loop? Okay, so suppose this is my circular loop, circular wire, in which the current is flowing in this direction. Suppose anti-clockwise direction, the current is flowing. Now my task or our task is to find the magnetic field at the center. So the point of consideration here is the center. Okay, understood? So if we want to apply the Biot-savart law, so according to the law we need to have a line element, right? Dl. So let us suppose the line element is somewhere here, dl. We have assumed the line element over here, and we have already discussed about the direction. So what is the direction of this dl? Along the tangent towards I. So at this point the tangent will be like this, right? So this is the direction, this tangent is the direction of dl vector, and this is the point of consideration, and this is the radius, this is the distance of the point from the line element. And according to the figure, this is obviously radius of the circular ring, and the direction of this radius vector or the distance vector is towards the point. So if you are able to understand the figure in this particular case, what is the value of the theta? So the value of the theta over here is 90 degree. What theta it is? I am talking about that theta which was used in Biot-savart law. The theta was the direct angle between the dl vector and the distance vector. So here the angle is 90. isn't it? Okay. So now let us, so what will be the magnetic field? So the magnetic field dB for this small line element dl will be mu0 by 4 pi, the current is small I indicated over here, I dl, sin theta is sin 90 by distance square. Now what is the distance here? This is capital R. So is this part clear to everyone? So I have just applied the Biot-savart law, for this particular case. Okay. Now this is not my result because this is the magnetic field due to this dl portion only. But we are trying to find the magnetic field for the whole wire, right? For the whole wire. So what we have to do? We have to perform the integration of this dV so that we can have the total magnetic field. Total magnetic field will be, magnetic field is represented by B. So B will be integration of dV. Okay, everyone. So just put the value of dV over here, mu0 by 4 pi I dl. Sin 90 is 1, so no need to write sin 90 again, and r square because sin 90 is 1. Okay, everyone. Now in this diagram or in this equation, dl is the parameter or dl is the variable. Okay, because dl is the thing which is changing. Except dl, if you look at this expression, all the things are constant because mu0 by 4 pi is itself a constant. I, the current in the loop is not changing, so the current will be same I, and the radius, the distance of the point from the dl is r. See, if you take the dl anywhere except here, without taking instead of taking dl over here, if you take the dl somewhere else, then also you will find the distance as r. So r is over here, it is also a constant. So you can take everything out of the integration. So let me write it over here. So your p will be, after this, mu0 by 4 pi, I is constant, r square is also constant, integration of dl. Right? And now this is a closed loop, the loop is closed, so you can use this symbol, closed integration of dl. That is a closed symbol, closed integration sign. We have used this symbol in Gauss law also. So mu0 by 4 pi I by r square into integration or closed integration of dl. So what is the length of this circle? Integration of dl means total length. So what is the length of this circle? Obviously it is the circumference. So the circumference is 2 by r. Okay, everyone. Now we have got the value. This to the cutting. We will get mu0 I by 1. This is the expression of B, which tells you the magnetic field at the center of a current carrying circular conductor. Okay, so if suppose there are n number of turns, I am taking here one turn. Suppose there are n number of turns, many turns are there, n turns are there. So if there are more than one turn, so the magnetic field for n turns will be simply n times. The turn number is multiplied. Okay, basically whenever there are more turns, then current is increased. More currents are there, so the current is actually increased by n times. So the magnetic field also increased by n times, as it is proportional to current. Okay, everyone, have you understood this derivation? Okay, then we will proceed to next application, that is the extended part or extended version of this, extended version. Okay, So in the next derivation, what we will find, we will take the point of consideration not exactly at the center but somewhere above the center, in the same line but somewhere above. Means if you take out this point towards you a little bit by amount a little bit height, okay, then basically it will look like a cone, right? Means this is a circle and the point is on the axis, it is at the axial point. Okay, so we will find the magnetic field for this case. Circular wire. Okay, so I hope you have understood the situation now. The situation I am going to now express by a diagram. Suppose this is the circular wire. Now think it in this manner, that it is in the plane. Okay, or sorry, it is intersecting the plane, intersecting the pole. And then this is the center, and from the center the point is somewhere here. Here the point, so this is the point 2. Okay, the point 2. So from the center or the distance of the point is suppose smaller. Okay, so we need to find the magnetic field at a distance r from the center. The radius of the wire, circular wire, is suppose capital R. The radius I am again taking capital R. Suppose the current is flowing in this direction. So if you imagine the diagram in 3 dimensions, so if I take the DL over here, so it will be in the direction actually towards you. It will be in the direction towards you, right? This DL is not in the plane of the board. The DL is outward, it is towards you. And according to Biot-savart law, we need to take the distance of the point from DL, right? We don't require the distance from the center. We actually require the distance from the line element, which is on the wire itself. So we are assuming the distance here is, okay, we are assuming the distance is. Now if you think this DL and this S vector, again they are perpendicular to each other, right? Because it is towards you, out of the plane, and S is in the board of the plane. So again here you will get theta as 90 degree. So the dB will be mu 0 by 4 pi. Suppose the current is I again, I current, IDL sin 90. Now the distance is what? Distance will be S square. Hopefully you have understood this part. Okay, how the angle is theta over here again. Okay, so again sin 90 is your 1. So you can write dP equals to 0 by 4 pi IDL by S. Okay, now one important imagination you need to do here. Okay, because I have already told you this kind of derivation is and direction is in 3 dimensions. There 3 dimensions are involved. So you need to imagine, you need to increase the imagination power, okay, so that you can think the image in your mind. So this DL is towards you, the S is in the plane, and we know the magnetic field vector is perpendicular to both S vector and DL vector, both the distance vector and DL vector. So as this is out of the plane, your B cannot be out of the plane. So B will be in the plane. B will be in the plane of the board, but perpendicular to S. So suppose this is the direction of B, that is DB basically. So this angle is basically 90. This angle is 90. Okay, because we know that DB magnetic field should be in the direction perpendicular to both this and this. DL is towards it, so this angle should be 90. Okay, this is the direction of DB. Now we will do what? We will do component division of this DB. Okay, so for component division I am taking these two axes. Let us assume that this DB is making an angle phi with the vertical. Okay, we are assuming that DB is making an angle phi with the vertical. So along this direction the component will be DB cos phi. Let me write it in paper. This component will be DB cos phi, and in this direction the component will be DB sin phi. Understood? Hopefully you have understood this component division of this DB. Now look at another picture of this diagram, another part of this diagram. Suppose you have another DL over here. Obviously it is a circular wire, so if you can take the DL in the topmost part, you can take the DL in bottommost part, exactly opposite to the previous DL. So for this DL also you will get the same value of the DB, because everything value wise everything remains same, but here this direction will be in this direction, making the same angle phi, because we have taken exactly opposite DL. So for this DB also you can do the component division. So in this direction DB component will be DB cos phi, and this direction another component will be DB sin phi. Now look at the broad picture of this thing. Okay, now look at the broad picture of this thing. So if we take another pair of DBs, suppose another pair of DL, suppose we take another pair of DL, okay, one here, one Y. So again you will have DB but in different direction. Okay, direction will be different. You can also resolve that DB in these two directions. When we will complete all the resolving of the vectors component wise, you will get equal and opposite component of DB cos phi for every pair of DL. Okay, so as for this pair we can say that DB cos phi component cancel each other because they are in opposite direction, and DB sin phi components are in the same direction, so they will be added. Understood my point? So DB sin phi will be added. So if we take any other pair of DL, for that pair, that particular pair, again the DB cos phi will cancel and DB sin phi will remain in the same direction. So we can conclude that the total DB will be, the total magnetic field will be integration of DB sin phi, not only DB but integration of DB sin phi. Now think if this part is clear or not. I have told many things by language, but whenever you are going to derive it on the paper, okay, on the answer script, you need to write these assumptions what I have mentioned. Go through the book very well. Okay, you will understand. There will be a paragraph written on the book about the thing what I have just discussed. Okay, so the conclusion is there will be DB sin phi component that will be available in the same direction, and DB cos phi will cancel each other for any pair. So we will get as a result the total magnetic field is integration of DB sin phi. Okay, is this part clear? Now rest is easy. Rest we have to do simple mathematics. Okay. found the value of dB na earlier. So if you remember, mu 0 by 4 pi I was small. Okay. Everything I dl sin a square. Now sin phi na. Let me write sin phi. So if this is phi, from the geometry you can say this will also be phi. Right? This is phi, this will be phi, because this is our total is 90. This is phi, so this will be 90 minus phi. This particular angle, this part will be 90 minus phi. So 90 minus phi plus phi will give you again 90. So if this is phi, this will be also phi. Okay. So from this triangle, what is sin phi? Sin phi is perpendicular by hypotenuse. Perpendicular is r, radius, and hypotenuse is s. Isn't it? So just put the value mu 0 by 4 pi I dl s square, and this is r by s. Okay. Again look at the expression. Leaving only dl, rest all the things are constant, because mu 0 by 4 pi is constant, I is constant, r is radius constant, and s is what? S is this distance. So this distance is also constant. If you take the circle like this, if you take the circular wire like this, and the point is somewhere here, okay, if you tie a thread from this particular point to each circumference of the circular ring, you will have the length of the thread same always. So this s is always same. So s is also constant. So you can write mu I r by 4 pi s cube integration of dl. Okay. Now again here this is the closed integration of dl. So whole integration of dl will give you what? Mu 0 I by 4 pi s cube. This is r, and this will be 2 pi r. Okay, circumference 2 pi into radius. So the final formula of d will be mu 0 I r square. If you cut pi by 2 s cube. S cube. S is hypotenuse na. From the triangle you can find s is how much? R square plus r square to the power half. From the triangle only we can find s is hypotenuse of this triangle, because we need to find the expression in terms of small r na. This distance is provided, so I have replaced s by small r. If this is s, s cube will be how much? R square plus r square to the power 3. This is the desired expression. Okay, understood? So do these derivations very carefully. Okay, and lot of things are there which you need to write in language. Okay, do not skip the writing part, because if you don't write the assumptions, then your marks will be deducted. Okay, so try to write the assumptions also. Okay, so we have got the formula for the magnetic field at an axial point. Okay, so again, if there are n number of turns, you can simply multiply with a capital N for n number of turns. Okay, so this is the formula. So this is what? This is the extended version of the previous one, what we did just now. If we want to go back to that part, to that derivation from this expression, how can we go? So earlier derivation was about the point which was at the center. So if you want to bring this point to the center, what change you need to do? If you want to bring this point P to the center O, you need to make r equals to 0. If you make r equals to 0, that means this P point is actually point O, which is center. So for center, r should be 0. Isn't it? For center, r should be 0. So if you put this value of r in 0. So mu 0 n I r square by 1. You are getting mu 0 n I by c. This is the same expression what we got from the previous derivation. So sometimes it is asked to find this derivation for the axial point, and from this expression to go back to this expression. Okay, so what you have to do, you just have to put r equals to 0. Then you will go back to the derivation of at the center. Okay everyone, so these are the two important derivations of applications, basically rather applications of Biot-savart law, which are usually asked in the exams, and you need to memorize the formula also, because depending on this formula directly you need to solve few numericals. Okay everyone, so do practice this thing at your home, because these are not so easy. So you need to practice this thing at your home several times, then only you will be expert in this part. Okay, otherwise this is not very tough, just simple derivations. Okay, this is very easy to score in your exam. This is all for today everyone, so we will meet in the next class.